Well, hello everyone. We are talking about Casey and Le Chatelier's principle. So we ended with this graph, which showed you this reaction. We have ethanoic acid, CH3COOH, plus we have ethanol, goes to form ethyl ethanoate and water. And here we started with no ethyl ethanoate or no ester. We started with some acid, we started with some alcohol, and eventually you can notice, look, here is a sharp falling off of our reactants. That means a steep reaction rate, a high reaction rate, and then we get to the reaction rate. Looks like it's stopped, but it's in dynamic equilibrium here when all the lines go horizontal. So how are we going to calculate Kc? Let's suppose they have a question which says find Kc for this reaction. So we write Kc equals, lovely unisex name, Kc. I bet there's going to be somebody who actually gives their child a name Kc, just the capital K and a small c. How about that? Shame, poor kids. I'm not trying to lumber that on you. Okay, Kc is going to be equal to products over reactants. That is basically what we're going to be doing. But don't write this in the exam, folks, but that's what in your mind you know is happening. The concentration of the products in moles per decimeter cube over the reactants. Okay, what is the product? Ethyl ethanoate. So we're going to put here our ethyl ethanoate. Well, let's write the formula. CH3COOCH2CH3. And there's a 1 there, there's a 1 there, there's a 1 there, and there's a 1 for our water as well. So we raise it to the power of 1. Every one of them has got a coefficient of 1 in front of the reactants and the products. Right, so we've got our products. We leave out the water. Why? Because water is a liquid. We leave out liquids and solids. What we're actually doing is we are actually, let's just move it along here and say Kc is equal to water, H2O, but this is going to become a 1. And our ester, ethyl ethanoate. Now let's take our ethanoic acid, CH3COOH, raised to the power of 1, water to the 1, ester to the 1, and there's our ethanol. This is a times, by the way, times CH3, CH3, CH2, OH. The square bracket means the molar concentration. Right, now let's go and give the actual values for all of these. Let's read it from our graph. Let's suppose that was 0, 0.1. Let's suppose this is 0.2. So our product at equilibrium is 0.2 raised to the power of 1, and our water is just 1 to the power of 1. We can ignore it, but let's put it in there. Do you see how 0.1, 0.2? Then let's suppose this is 0.3, and let's suppose that is 0.4. 0.4. So we've got 0.3 and 0.4. Okay, so we've got our acid at the bottom, ethanoic acid there. So what is the ethanoic acid concentration? It is 0.4, right? So it's going to be 0.4 raised to the power of 1 times. Now let's have a look at B, which was our ethanol. Remember, B was the ethanol. What is B? We're reading it off. At equilibrium, where the line goes horizontal, it's 0,3. 0,3 raised to the power of 1. Right, let's get our calculator. Here's our calculator. And let's type in the values. Okay, so what have we got? 0.2 raised to the power 1 is just 0.2. Divided by, open brackets, 0.4 times 0.3, close brackets, and our answer comes to 1.67. So there's our Kc is going to be 1,67. Easy enough? So when they give you values like this that you've got to derive from a graph, and they say find the value of the equilibrium constant Kc at time 2 minutes, which is there, what do? We look for where it goes horizontal, and now we plug in the values of the products over the values of the reactants. So there is the value of Kc, no units. We worked it out from our graph. I love graphs. They basically, daddy, tell us a story. Okay, once upon a time there was a product. At time 0, there was no product. And after 2 minutes, there was 0.2 moles per decimeter cubed of product. My son. And then there was a high amount of acid and alcohol. And after 2 minutes, there was 0.4 moles per decimeter cubed and 0.3 of our acid and our alcohol respectively. That's what our graph is telling us. And look, the graph goes flat, so that tells me that the rate of the forward and reverse reaction is the same. The concentration of reactants and products is not changing. And therefore we write our Kc expression, we plug in the values, we turn the sausage machine handle, and out comes our value.